Another and hopefully an interesting and useful list of crash courses for Orgo 1. 1IH NMR, hydrogen proton NMR. So a lot of struggle students have with this is that there's actually 3 pieces of information contained in any NMR signal, so any peak we receive. And it gets hard because they kind of get this information mixed up, they forget what information corresponds to what. So I've got this simple example up here. We're going to treat the R groups as something like a terp-butyl group, so there's no hydrogens associated with them. And we'll talk about more when we get to J coupling why that's important. So the 3 pieces of information contained in any signal you get from an 1H NMR spectrum. The first is the chemical shift, delta. The chemical shift is going to describe how shielded that proton is. Now, more specifically for organic, we're going to use the chemical shift as a way of guessing what the functional group probably is. And I say guessing because there are a lot of functional groups that share common overlaps. In the case of these 3, they actually will probably sit between the 0 and 2, if not the 0, 3, 0, 3, 4 ppm range. So it's not diagnostic, it's not proof, but that's not what you do with NMR. What you do with NMR is you're looking for a self-consistent solution, something that makes sense in terms of what you're seeing. So in terms of this, I have 3 hydrogens as drawn. I've got a blue hydrogen, which is going to be the most deshielded. This is next to the fluorine. 2 black hydrogens. They're going to be moderately deshielded because they're next to the fluorine, but they're not connected to the fluorine. And then our red hydrogens here are going to have the most shielding because they're the furthest away from the fluorine. Again, I'm not going to specify what these R groups are. We're just going to treat them like they don't exist. They're just there to get rid of our hydrogens. So that's piece of information 1, chemical shift. Piece of information 2 is the integrated area. Now the integrated area, assuming it doesn't become a simplified ratio, which it does for most NMR software, but skip that. If you do simulation software, they'll show it to you. The integrated area tells us the number of protons, the number of hydrogens with that particular chemical shift. So if we look at this diagram, there are 2 red hydrogens. So if we integrated the area, we would get 2. If we integrated the area here, we would get 2. And if we integrated the area here, we would get 1. Now, these integrated areas are associated with this chemical shift. They tell us the number of hydrogens that have that particular chemical shift. So this is specific to the particular carbon atom we're connected to. That's the second piece of information. The third piece, which is the hardest to work with, is the J coupling. What the J coupling tells us is how many hydrogens are on the adjacent carbons. So with the blue peak, how many hydrogens are on the carbons connected to that particular blue carbon. So if you look at it here, this hydrogen sees 2 black hydrogens and that's it. It's always 2 plus 1 for the splitting pattern, so 2 plus 1 is 3. So we would get a triplet for this particular hydrogen. So we're getting 3 because it sees 2 on the nearest carbon. Red will see the same thing. There's 2 neighboring hydrogens, and so red's going to be split into a triplet. Hard part here is the black carbons, because the black carbons actually see 2 different types of hydrogen. They see the 2 red hydrogens, so there's going to be a split due to that, and it's going to have its own coupling constant. And there's going to be a split due to this hydrogen because it has its own coupling constant. Now, these were exactly the same. So 2 hydrogens, be a bit more complicated what's going on, but let's stick to this. These are going to be by themselves. The red hydrogens, if we ignore this one, would split this into a triplet. If we ignore the red hydrogens, the blue would split the black into a doublet. So we're actually going to get both effects. We're going to get a triplet and a doublet. So we can call it a doublet of triplets or a triplet of doublets. And what you're going to get is this weird kind of noisy shape going on at the bottom. Now, in principle, you could try to figure out what it is. Probably what you see is a triplet of doublets written inside of a table to let you know that the triplet means there's 2 nearby on one carbon, the doublet means there's 1 nearby on another carbon. So this is the crash course in how NMR spectra go. The reverse engineering is the number of peaks you see should correspond to the number of different hydrogen-containing functional groups. The area should tell you how many hydrogens are on those functional groups, and ideally what the splitting patterns let you do is try to figure out how those functional groups are connected to each other. If we had this molecule, for whatever reason these R groups contain no hydrogens whatsoever, we would be able to say that, well, these 2 have to be near these 2. That's why this splits into a triplet. This has to be near this one, that's why it splits into a triplet, and this has to sit between the 2 because we see the effect of these 2 and this 1. So There's your crash course on NMR, or at least 1H NMR.